In this example, the switch was connected to this point for a very long time, and at time 0, what we do is we open the switch, and then we end up with an RL circuit in here. And what we're being asked to compute is the Vx across here, across that 6 kilo ohm resistor. So I went ahead and I just basically copied the equation that we know about RL circuits, and I'm just going to put them here for reference. And what we need to do is, what we're being asked to compute is either the voltage in here or maybe the current across it, and because we know the 6 kilo ohms, we can figure out what the voltage is. So what I will do is I'll try to find the current across the inductor, and to find the current across the inductor we need a few things. First, we need the initial current flowing through that inductor, and then we're going to have to compute the tau in here. So let's get started with the I0. And I0, usually it's the initial current flowing through that inductor. So typically we compute it using the before switching, because right before or right after switching or at switching, the current cannot change instantaneously. So if we compute it in the steady state before switching, it becomes easier. So the way we compute it is usually we say, well, the switch was here, and if we stay for a long time, 5 taus to be specific, that can be treated as simply a wire. And what we're interested in is computing the current, I'm going to call it I0, flowing through this. It's I0 because it will be the initial current flowing after we switch. So that's what we're interested in computing, and there's multiple ways we can compute them. We can combine these two in series, use voltage division to figure out what the voltage in here is, or I can just go ahead and just tell you, you know what, let's write nodal equation at this particular node. So, and I'm just going to call this particular node as maybe V1, let me just call it that way. So V1 minus 12 divided by 3 kilo ohm plus V1 divided by 2 kilo ohm, because this does not exist, it's just a wire, so it's V divided by 2 kilo ohms, plus I believe it will be V1. Actually, this is the same as Vx, so why don't I just do that in here? So I'm just going to call it, instead of V1 and V1 in here, it is actually Vx. That's what we're after. This is Vx, and this is Vx before switching, and this is Vx, and this is Vx. Before switching, Vx basically appear in here because this is a wire. Okay, all right, so that's Vx divided by 6 kilo ohms equals 0. So that tells me what the value of Vx before switching. What we're interested in is what happens to it after switching. So this is just the Vx before switching, and that should give me the following value. That will be exactly 4 volts in here. So we have it as 4 volts. So we can technically figure out what this current in here is, and that current in here, which I'll call I0, is just simply will be Vx before actually switching divided by 2 kilo ohms, which is simply 2 milliamps. So that's basically the value of I0. So we were able to figure out what the I0 is. Now what we need to do is we need to figure out what tau is, and tau is just simply L divided by R. Okay, that's the time constant. Let me just draw that circuit here. So that circuit will appear something like this here, like that, and then we have the inductor. Okay, and then what we have is in here is 6 kilo ohms, and we have 2 kilo ohms in here. Okay, and we have 2 millihenries. That's what we have. Okay, so the RL, basically we have to end up with a circuit that looks something similar to this here. It has to have one inductor and one resistor. That's how we have in terms of RL circuits, in terms of natural responses. So the R shouldn't be the 2 kilo ohm or the 6 kilo ohms. It's actually the combination of the 2 and the 6, which combined it will be 8 kilo ohms. So if I'm computing the tau, it just will be 20 times 10 to the negative 3, because I need to convert it to henries, and that will be 2 plus 6, which is 8 times 10 to the power 3, because I have to convert it from kilo ohms to ohms, and that will be tau, which is in second, and that value would be 2.5 times 10 to the negative 6 seconds, or the 1 divided by tau is simply 1 divided by tau. It's actually 400,000. 400,000, well, second minus 1. All right, now all we have to do, we have the I0, we have the tau. All we have to do is just basically plug it into this equation to figure out what the current that we are computing is. And just to indicate the current directions and everything, so what we will do is we will say that this one here is I0, so this will be negative, this will be positive, because remember, initially when we talked about this one here in red, that was the positive, that was the negative, and we've said that the initial current is going that way, and the current that I'm interested in this way. I just basically flip them now, so that will become IL of t. Okay, so all I have to do is just substitute these values, and these values would be simply 2 milliamps. Okay, since this is in milliamps, the whole thing will be in milliamp, e to the negative I believe that will be 400,000 T, and that's for T is greater than or equal to 0, and that's milliamp. Okay, so that's the IL of T. So that's the current flowing that way through the 6 kilo ohms, through the 2 kilo ohms, through the 20 millihenries. All right, so what we're being asked to compute, if you remember in here, is actually this one here, plus minus V of X, okay, after switching. So there's multiple ways to do that. We can either figure out what the voltage across that inductor is using this equation, for example, okay, or and then we apply voltage division, because it's I know the voltage across the inductor is, and 2 kilo ohms, 6 kilo ohms are in series. We can apply voltage division. Just pay attention to the fact that you have to use a negative, because this one here is positive, negative, this one here is negative, positive. Or much simpler, well, I know the current flowing through a 6 kilo ohms, and I'm interested in the voltage across it. I can just basically directly say, well, V of X of T after switching is just simply negative 6 times IL of T. And the negative happens because this particular current is hitting the negative port in here, so passive sign convention tells us that we have to put negative. So that will become negative 12. I believe that will be 6 kilo ohms, and this is milliamps, so this is in volts. That's fine. Negative 400,000 T, and that's for T is exactly greater than 0, and that's in volts. Why is it greater than 0? Because if you substitute T equals 0, you're going to get V of X 0 plus, because this is after switching, you're going to get negative 12 volts. And we know that before switching, that V of X happened to be 4 volts. So it actually jumps from 4 volts all the way to the negative. Let me just double check. Yes, it jumps basically from 4 volts to negative 12 volts. So that was here, just to be sure. This says here is just simply V of X at 0 minus, and that happened to be 4 volts in here. Okay, so that will be the voltage that I'm after.